So here we have section 7.5, which is basically summary and strategy for integration. Now, of course, there's no substitute for practice and experience, and just reading this list probably isn't going to give you the feel that you need in order to do most integrals, but let's recap. The techniques we have available are U substitution. We have integration by parts. We have techniques for trigonometric functions. And we have trigonometric substitution. Which I mentioned when I made that video, that basically what you're looking for those is a sum or difference of squares. And after that, we had partial fraction decomposition. Now, lots of problems are going to need some combination of all of these techniques. And to save time, I'm just going to refer to each of these techniques by their section numbers. So this was 5.5, 7.1, 7.2, 7.3, and 7.4. So some guidelines. First, we're going to have some kind of an integral, and we're going to want to look at it. If it's a rational function of polynomials, then we're definitely going to go for 7.4. It's possible that one of these problems doesn't need 7.4 because there are some special cases which use 7.3, or you may even get luckier and you just have to use 5.5, or maybe it's just a basic antiderivative. And sometimes a U substitution is necessary first. I might have something which looks like a rational expression of polynomials, but instead of actually having powers of x, I've got powers of sine of x or something. I have something kind of nasty looking, but I'm able to do a U substitution, and that turns it into a simpler looking problem. If it's a product of trig, or of trigonometric functions, then we know we're going to be headed towards 7.2, but you're going to want to think about all the trig identities. This is going to be, double angle formulas, half angle formulas, which are actually some of the techniques out of 7.2. Maybe sum or difference formulas, and certainly some of the more basic ones like the Pythagorean identities, or the basic identities like sine, like secant, which is equal to 1 over cosine, or tangent, which is equal to, what did I just say? The basic ones like secant, which is 1 over cosine, or tangent, which is equal to sine over cosine. If you're not sure what to do with things first, maybe start off by considering changing everything into terms of sine and cosine. the basic goal, the real goal of these, if we don't notice something we can do earlier, is to try to get basic functions, sine of just a single variable, nothing fancy. If there is a sum or a difference of squares, then chances are we're going to be doing a 7.3 problem, trig substitution. Sometimes you might have to make a sum or difference of squares. So you might have to do some legal algebra, or maybe some really funky stuff like, oh, I have an x, but I'm going to look at it like the square root of x instead, and try to do a u substitution to make it look more obviously like a 7.3 type of problem. Now, if I have is a hard function alone, or a, oops, I keep saying of, or a product of different functions, then we're going to be looking at 7.1 a lot of the time, possibly 5.5. These are these could be your last case attempts at trying to do the integral, although a lot of times you're looking for a u substitution to do first before you try to look for some specific techniques. So there's really no substitute for preparing for integrals than just hammering through all of the exercises in section 5.5, 5.5, 7.5. And if you get bored with those, or those aren't hard enough, then go to the library, find a different book, and do all those problems too. So now what I'm going to do, just so that we have some idea of what kinds of things to look for, is I'm going to show off for a bit of some functions that I particularly chose out of the book. 1. Let's say I had the integral of x squared divided by x to the 6th plus x cubed plus 1 dx. This is a rational function of polynomials. So my first thought would be to go to, hey, if I have a rational function of polynomials, that means I could do partial fraction decomposition. But how do I factor something like that? That's x to the 6th. We run out of formulas describing roots of polynomials at x to the 5th. So I'll stare at it and I think about it a little bit, and I see, well, hey, this is like x cubed squared, and that's just x cubed. And x squared is practically the derivative of x cubed, so I'm going to try to simplify my problem by doing an initial u substitution. Let me label that. U would be equal to x cubed, and my du would therefore be equal to 3x squared dx. So I should have 1/3 let's see if I do this right, of 1 over u squared plus u plus 1 du. And don't forget, sometimes when you're doing u substitutions, that you can solve for the x from the initial u substitution to maybe help clean up a little bit. And there's definitely some we're going to have to do that with. So this integral, now that I'm looking at it, I see u squared and a 1, so I want to think about arctangent, but I've got this u that's in the middle. But it is a quadratic, so what I'm going to try to do is complete the square on that. And see what that gives me. 1 over, see if I had u squared plus, this is 2 times 1/2 of u, so I'm going to add 1/4 and subtract 1/4, and there's a plus 1 way out there, and du waiting patiently at the end. I have 1 over, so this part turns into u plus 1/2 quantity squared, and then I have a minus 1/4 plus 1, so this is a plus 3 over 4 du. Now this looks a lot more like an arctangent problem. Now you could approach this with, since it's a sum or difference of squares, this being here equal to the square root of root 3 over 2 quantity squared. I could treat this as a 7.3 problem. I could try to do trigonometric substitution. But since I have studied reference page 6, I know off the top of my head what this integral is going to look like. But just so that I'm careful, I'm going to do another u substitution to clean up what's the variable squared part here. So I have a w equals u plus 1/2, which means dw equals du. So I have 1/3 integral 1 over w squared plus 3 over 4 dw. So this antiderivative is 1/3 times, that's supposed to be a squared, so that's the root 3 over 2 quantity squared, so this is 2 over root 3, arctangent of 2 over root 3 times x, not x, w, plus c, and I'll undo my substitutions, 2 over 3 root 3, arctangent 2 over root 3 times u plus 1/2 plus c, and my u was x cubed. So let's see, you can check me on that initial antiderivative by comparing it with reference page 6. But you can always check the rest of your answers by taking the derivative. Fundamental theorem of calculus, guys. If I could take the derivative, I should get back to my original problem. I might have to change some stuff after I first take the derivative to make them match up. So let me add something to the 7.3 note here. Sometimes it is well hidden. So sometimes I want to look for square roots. And the reason I say that is this very next problem. I chose it specifically for this. if I have 1 over x times the square root of 4x plus 1 dx, I want to try to integrate this. Now, u substitution won't work. Actually, I can probably think of two different ways to do this. Now that I mentioned u substitution, if I said u was equal to 4x plus 1, no, square root of 4x plus 1, then let's see here, my x would be equal to, I have u squared equals 4x plus 1, which means that x is equal to u squared minus 1 divided by 4. Okay, and my du here would be 4 over 2 square roots of 4x plus 1 dx, and I could cancel that and just have a 2 on the top. So when I factor this, when I substitute this, I'm going to have a 1/2 an integral. The dx divided by the square root, that's my du. And I'm left with an x over here. But x is equal to u squared minus 1 over 4. So this is u squared minus 1. Divided by 4, so I'll put the 4 up there. So I've turned this weird looking square root thing with the nice u substitution, where I didn't even use the u directly at all, and I got a nice partial fraction decomposition problem. So this is now 2, because the 4 comes out, 1 over u plus 1 times u minus 1 du. So that should be equal to a over u plus 1 plus b over u minus 1. So au minus a plus bu plus b would have to be equal to 1. Which means that a plus b, there's no u term over here, so this is equal to 0. And b minus a would have to be equal to the 1. So a equals b. No. B equals minus a. That's from the first one. So I have minus 2a equals 1, which means a equals minus 1/2, which means b is equal to positive 1/2. So I can replace that problem with my partial fraction decomposition, and I'll have minus 1/2 over x plus 1, not x, u plus 1, plus 1/2 over u minus 1 with a du. To make things nicer, I'll redistribute my 2 inside, so that it looks like I end up with u minus 1 minus 1 over u plus 1. And those have easy antiderivatives. This is the natural log of absolute value of u minus 1 minus natural log absolute value of u plus 1 plus c. Or, if I like being condensed, natural log of u minus 1 over u plus 1 plus c. But what was my u? My u was the square root of 4x plus 1. So the natural log, the square root of 4x plus 1 minus 1 over the square root of 4x plus 1 plus 1 plus c. Just for good measure, I'm going to try that one a different way now. So I guess this is 2b, and the other one was 2a. So I mentioned with the trig substitution that I might have to make my own sum or difference of squares. And what I mean by that, here I have a nice square root. Great. But here, for x, I could read, for whatever reason, as 2 times the square root of x, quantity squared. And out here, this x would likewise be the square root of x, quantity squared. So I could say, oh, well, I'll let u be equal to 2 root x. Then my du is equal to, well, 1 over the square root of x, dx. And so when I make that substitution, let's be careful with this. Square root of x, square root of x, square root of 2 square root of x squared plus 1 dx. That's what I had suggested. So one of these root x's with the dx becomes the du. So this is equal to 1 over, I'll have the square root of u squared plus 1 du. But over here, I need to get rid of an extra x, or extra square root of x. But the square root of x would be equal to u divided by 2. So this is equal to 2 over u square root u squared plus 1. Now I definitely have a sum or difference of squares, so I'm going to set up a trig substitution. Let's see, the u squared, this is a sum, so I need a u, a 1, and a u squared plus 1. I like tangent, so let's let this be my angle theta. That way tangent of theta is equal to u divided by 1. So if I take that derivative, secant squared of theta d theta is equal to du. And just for good measure, the hypotenuse divided by the adjacent would be secant of theta. Hypotenuse over adjacent would be u squared plus 1, well, divided by 1. So when I substitute everything, the 2 stays, the du turns into secant squared theta d theta, the u turns into a tangent of theta, and the square root of u squared plus 1, looks like I made a mistake here. Hypotenuse squared is the sum of the legs squared, so the secant is the square root. So I don't need a secant there, I need a secant here. Got to be careful with these things. So that secant cancels with that secant. I have the integral of 2 secant theta over tangent theta d theta. So this is turned into a 7.2 problem, it looks like. I have 1 over cosine, 2, I'm going to change everything to sines and cosines, see if I can fix it. It looks like the cosines cancel, and I'm left with the sine on the bottom. So this is equal to the integral of 2 times cosecant of theta. Now, this is also on reference page 6. You can do this with a very clever u substitution, or maybe even integration by parts. But this is going to be 2 times the natural log of cosecant theta minus cotangent theta. It's a lot like the integral for secant, actually, plus c. But what was theta? I need cosecant of theta, that's hypotenuse over opposite, and I need cotangent of theta, which is adjacent over opposite. Cosecant. Cosecant is hypotenuse divided by opposite. So I have the square root of u squared plus 1 divided by u. Minus cotangent, opposite over adjacent. No, adjacent over opposite. That's going to be 1 over u. Adjacent over opposite. Yes. 1 over u plus c. But what was my u? Well, my u was 2 times the square root of x. This is 2 natural log square root of 4x plus 1 divided by 2 root x minus 1 over 2 root x plus c. Now you might be thinking, well, this looks a heck of a lot different from the other one. Let's see if we can't make them match up. So this usually ends up being a lot of work, but if we take this one right here and distribute the 2 that's a coefficient as a power on the inside, we're going to get the natural log of square root of 4x plus 1 minus 1 squared divided by 4x plus c. Now the answer I had before was 4x plus 1 minus 1 over 4x plus 1 plus 1. So if I were to take this problem over here and multiply and divide by the conjugate, I would have the natural log. The conjugate of the bottom is the square root of 4x plus 1 minus 1. So I'd have the square root of 4x plus 1 minus 1 squared divided by, when I multiply out this conjugate, I get 4x plus 1 minus 1. And those cancel. And you can see these now match. I should have been using vertical bars. So sometimes you can get really different looking answers when you finish these problems, but with maybe a lot of work, they end up looking exactly the same. Number 3. This one is similar to the previous. I had the integral of the square root of x divided by 1 plus x cubed dx. Then what do I have on the bottom? I have the sum or difference of cubes, which does not fit one of my techniques above. I can factor 1 plus x cubed. That's pretty easy. But the thing on the top is a square root, which doesn't help me for partial fraction decomposition. But this is actually a lot like the previous problem where, well, I don't have the sum or difference of squares, so I'll try to make one. This is either one of the previous problems. I try to get the right u substitution going. Since I have a square root of x up here on top, I'm going to consider square roots in place of the x on the bottom. So this is equal to the integral of the square root of x divided by 1 plus, I could say, the square root of x to the 6th dx. Or I could say this is the square root of x over 1 plus the square root of x cubed squared dx. And we've done enough problems to recall that, hey, the derivative of x to the 3/2 is x to the 1/2. So if I say u is equal to the square root of x cubed, which is equal to x to the power of 3/2, that means du is equal to 3/2 x to the 1/2 dx. This changes my integral with a u substitution to look like the integral of 2/3 of the integral. The square root and the dx become the du, so I have 1 over 1 plus u squared du. And I've seen that integral enough times, it's one of our favorites. This leaves me with 2/3 arctangent of u plus c. And the u is, of course, x to the 3/2. This is 2/3 arctangent x to the 3/2. Or x root x, or the square root of x cubed. However you want to write it. Let's try another one. Number 4. This one looks pretty crazy. I have this integral of x times the square root of 2 minus the square root of 1 minus x squared dx. Which looks wonderful, right? I have a square root inside of a square root. There's no way I can pull this off. Unless we want to be familiar. We want to see that, hey, I have a 1 plus x squared and I have an x out here. So I'm just going to start off by doing a u substitution. Maybe it'll make my life easier. U equals 1 minus x squared, so my du is equal to negative 2x dx. This changes my integral with a substitution to negative 1/2 integral square root of 2 minus root u du. And now I've still got a square root inside of a square root. So I think what I'm going to do is treat this like the previous two problems and try to force myself to have a sum or difference of squares. I'll say w equals the square root of the square root of u, or the fourth root of u, or u to the 1/4. Then my dw is equal to 1/4 times u to the negative 3/4 dw. No, u. Which is 1/4 times 1 over u to the 3/4, which is du, which is the same as 1 over 4 times 1 over the fourth root of u cubed. Which means if I solve for the du here, I'm going to have du equal to 4 times, that's w cubed dw. This turns into negative 1/2 integral square root 2 minus w squared multiplied by 4w cubed dw, which means I've got negative 2 integral w cubed square root 2 minus w squared. So what I would do here, I could do one of two things here actually, now that I'm thinking about it. Integrals are lovely like this. There's always some other kind of different path you can take. So A, I could set up a trig substitution where I'd have the square root of 2 on the hypotenuse, a w on the side, and the square root of 2 minus w squared on the bottom. Or B, I could say a triple u substitution. A triple u? Like that? No. Why don't we just use the letter r? R equals 2 minus w squared, which means that w squared is equal to 2 minus r. I know I'm going to need that because the derivative of w squared is only going to take care of one w out here, but I'm still going to have a w squared left over. My dr is going to be negative 2w dw So my negative 2 integral w cubed is now w squared times w times the square root of 2 minus w squared dw. So what do I got? Here's my minus 2. Here's my w. Here's my dw. This is my dr. My w squared is 2 minus r. And this guy is r. So if I complete this substitution, I'm going to have the integral of 2 minus r times the square root of r dr, leaving me with the integral of 2 root r minus r root r. And I can do that integral just fine because that's just the power rule. That's r to the 1/2 plus 1 is 3/2. So that's 2 times 2/3 r to the 3/2 minus, that's r to the 3/2, so that's 2/5 r to the 5/2 plus c. And then I gotta undo all of my 3 substitutions. R equals 2 minus w squared. W is equal to u to the 1/4. And u is equal to 1 minus x squared. Let's try to keep track of that. R equals 2 minus w squared. W equals u to the 1/4. U equals 1 minus x squared. Which means this is equal to 4/3 times r, which is 2 minus the square root of 1 minus x squared to the 3/2 minus 2/5 2 minus the square root of 1 minus x squared to the 5/2, and there's supposed to be a plus c fitting in there. Let's go ahead and finish. Do a little bit more work on this trig substitution I have on the left. Opposite over hypotenuse, that's a sine. Sine of theta is equal to w over root 2, or w equals root 2 sine of theta, which means I have negative 2 integral square root of 8 sine cubed of theta times the square root of 2 minus 2 sine of theta, sine squared of theta, times the d theta. I need a d theta. dw is going to be, need to multiply, square root of 2 times cosine of theta d theta. And if we work this out just a bit more, I'm going to have negative 8 times the integral of sine cubed of theta times the square root of 2 times cosine squared of theta d theta. And that is a standard 7.2 problem. I move the root 2 out, I'll change 2 of these signs over, and then I'll have to undo all those substitutions. It might be worth, yet again, going back to this problem and trying to do a trig substitution. Since there's a sum or difference of squares here, try to do a trig substitution right in the beginning. But I think you might end up having to do 2 of those at once. Or maybe you'll just get something that you get stuck with. Who knows? Finally, let's have the integral of the natural log of x plus the square root of x squared minus 1 dx. Again, here, I have a sum or difference of squares, so I might as well just start off with the trig substitution, because I don't see any other chances of anything else. I can't do partial fraction decomposition. There's no fraction. I could try to do integration by parts, but I don't even want to take the derivative of that. And I'm lazy. I could try to do U substitution, but I don't see any good choices to set up a U substitution. I don't think it's going to make my problem feel any better. And there's no trig. So, for lack of a better option, I might as well just go ahead and try the triangle. The x squared comes first, so I have x here, a 1 here, and the square root of x squared minus 1 down here. I'll put my angle up here, because then the secant of theta will be equal to hypotenuse over adjacent, which is x. And if I take the derivative there, I'll have secant theta tangent theta equals dx. Oops, forgot my d theta. So if I do that, I have the integral, I have the natural log, I have x is secant theta, plus, let's see, square root of x squared minus 1. That's opposite over adjacent. That's actually tangent of theta. And the dx out here is secant of theta tangent of theta. D theta. Now this guy, I recognize this guy because I spent so much time on reference page 6, guys. This right here is the antiderivative of secant of theta. So now I'm going to use an integration by parts. This is a weird problem because I needed trig substitution to set up an integration by parts for me. And I know that this guy is the derivative of secant of theta. So I'm going to say that u equals the natural log of secant plus tangent so du is equal to secant of theta, d theta. My dv is equal to secant theta tangent theta d theta. So my v is equal to secant of theta. So this integral is equal to uv secant theta natural log of secant theta plus tangent theta minus the integral of v du secant squared of theta d theta, but that is the derivative of tangent. So all I have to do now is undo my thetas. Well, secant of theta was equal to x, tangent of theta was equal to the square root of x squared minus 1. So this should be an easy unsubstitution of x, natural log of x plus the square root of x squared minus 1 minus the square root of x squared minus 1 plus c. So one of the difficulties with math is the need for creativity. Don't be afraid to experiment with some of these, but definitely spend the time practicing them until you build up some kind of an intuition for dealing with some of these problems. Some are certainly worse than others, but you really do need to spend the time on them.